Thanks for the invitation. I'll probably be the only nuclear physics talk that's here. I'm going to tell you a bit about what we're doing. This is my team. Thomas Dietrich, who's currently at the Czech Republic, along with his colleague Daniel Lager. Myself, Christina Loney, who's currently with me. Both of those are former students, and this is the teamwork group, postdocs and students associated with the project. Alison Dreyfus, for the benefit of the NSF folks in the crowd, was a former REU student. Robert Baker from Austin P, and then I've always had a cadre of internationals, in this case a couple guys from Armenia. And this was the work that's done here was also part of a PETA-APS proposal supported by the NSF, as well as a DOE EPSCoR proposal supported by the DOE, of course. So physics of the atomic nucleus. Over here I've shown the phase diagram. Quarks to cosmos literally, but if one is interested in nuclear physics, you're interested in where the quarks condense to form nucleons, and the nucleons bind to one another, which produces nuclear matter. Here's you've got two nucleons forming the beginning of a system. If it's just two, it's a deuteron, of course, but all of the systems are formed in this way. We start with the nuclear interactions. It's a residual strong force, one of the four forces of nature. It's highly complex. We don't know a whole lot about it. We do know that it has 2, 3, and 4 body parts, and you'd like to start with QCD and actually produce nuclear interactions, and from those actually build nuclei. That's the name of the game. Why is it interesting? 98% of the mass/energy of the universe is in nuclear matter, so it's pretty doggone important. There we go. So the applications of nuclear structure and nuclear reaction modeling, astrophysics, of course, we've heard about that. Here's the chart of the nuclei, and how that gets built is all nuclear material. Neutrino and cosmological research, here's the standard model, here's neutrino studies, here's dark matter studies. This, of course, is at the more practical level, that's NIF at Lawrence Livermore National Lab. This one I like to show for students when I give it to them. What is a strong interaction? It comes to you in many ways. This does happen to be LSU. LSU does play football, even though the SEC didn't win this year round. It's a strong interaction, but there's many body dynamics associated with it, and there's nuclear reactions. And all of those you get in studying the structure of matter, of nuclear matter in particular, and that's what we're interested in doing. So basically, what does it boil down to? It boils down to a Hamiltonian theory. That's where the Hamiltonian axon and axon basis states to form a matrix, and ultimately you're going to solve a large matrix. And this just shows you illustratively that the matrix that one forms with an embedded Hamiltonian, which is of a 2 plus 3 plus 4 body form in a many-body system, is typically relatively sparse. And the whole idea is to get from that information which tells you about the ground state properties of nuclei, including their shape, which is what I've tried to portray here. There's one problem. Nuclei, if you want to model the theory, you have to start with something that you can, the box that you can put it in. For nuclear physics, that's the three-dimensional oscillator. It's the only choice you really have if you want to eliminate spurious center of mass motion. You can do it exactly with the harmonic oscillator. So all you can do is populate levels, and we call these the major levels of the oscillator as you go on up. The first ab initio calculations of nuclear structure really tracked with the beginning of high-performance computing. I've spent a great deal of my life before 1985 working through theoretical models and developing algebraic theories. But once 95 up in 2000, you began to see the possibility of really modeling these things in all their glory. Here, what I've done is showing you this is dimension versus the number of excitations of particles up. And you'll see that it's a combinatorial problem if you do it in the simplest form. And you'll see this is 10 to the 10th. It doesn't show up with very high resolution here, but that's about it. Maybe you can get 10 to the 10.5, but that's the largest supercomputer that exists. So you are limited, and these show various nuclei and how high you can go and what you can study. And basically, with ab initio theories, that's starting with QCD, taking your interaction, diagonalizing it, you have choices: quantum Monte Carlo, lattice effective field theory, so on and so forth. The no-core shell model is the one that was brought to the forefront by James Very and Bruce Barrett and collaborators. But you hit the wall on what you can do, and I want to show you that if you think about the physics a little bit, you can probably do a little better than that. So the number of harmonic excitations I talked to you about, it is a harmonic oscillator, three-dimensional harmonic oscillator. But there's a partial symmetry. We all, at least those of us who grew up physicists, learned that symmetries are important. There's exact symmetries and there's partial symmetries. Both can be very important. Exact symmetries are like rotational invariance, time reversal invariance, so on and so forth, non-parity violating type interactions. But there's other symmetries that are partial. And in nuclear physics, if you just study a few nuclei, you see that once you get just a few nucleons, they start showing deformation. It turns out that that tracks with Su3. The 3 is the 3 dimensions of the oscillator. So you can organize your basis states according to symmetries which have exact symmetries like rotations, but they also have partial symmetries like deformation. So you can take that huge space and you can gather it, if you like, organize it by symmetries. And in the case of Su3, that's what we did. The computational effort that involved, just tell you here, it's about 95% computing matrix elements. 3% is in the eigenvalue problem. And this is how it looks if you actually do it. It's I said embarrassingly simple, but you offered it was. Okay. Okay, I like that better. The actual code that we've developed is Su3 Shell. It's a generally available, everything we do, all the data we input, all the data we get out, the codes themselves as they're being developed are all in the public domain. And you'll see, although this is a low number of nodes, you'll see that it scales very nicely, and we've now pushed it up to 10,000, 100,000 beyond, okay? And it scales very nicely. What do you get out? Here we've organized the basis by all possible configurations that you can have, and you say that everything lines up along one edge, which is the edge of maximum deformation and least spin. Pleasant surprise for us. This is a little retro. I thought you might want to see what an IBM card looks like if you haven't ever punched one yourself. It's not quite that. It's actually all possible configurations where the size of the configuration, if everything were equal, is proportional to the log of the dimension, it's the size of the dot. So that's if everything is possible. There's no underlying symmetry imposed on it. But here's what actually happens. This is the case for lithium-6. This is equal probability. And the ones that actually come into play for various states, 1 plus, 3 plus, 2 plus, second one plus, you see that it's all pushed to the right. Maximum deformation, minimum spin. And that's with the full ab initio Hamiltonian. Here's another case. This is, whoops, it's oxygen 16. The 16 is blocked. But again, equal probability, here's what actually happens. So there is a partial symmetry that's very effective in organizing your model state and telling you what's going on. With that, you can do other calculations, neon 20, which is much higher than no-core shell model folks have been able to do. Complete space is 10 to the 12th. If you actually use the fact that there's an effective symmetry, you can bring it down to 10 to the 7th. What's that? 5 orders of magnitude? That's a huge savings by using a little bit of physics. And you can actually see what the structure of something like neon is. Here's one that nobody has been able to touch. And you'll see the exponential growth, but the population is very small. This is for silicon-24, which is also a nucleus of interest in nucleosynthesis. So what have we been able to do? We've been able to go beyond the no-core shell model into what we call a symmetry-adapted no-core shell model. It's a little more structure, has a whole lot of Klebs-Gordon and Rocca coefficients if you want to know the real language. But it doesn't matter. It allows you to move up a long ways in terms of the type of nuclei that you can study. And you can make predictions about and map onto what experiment does. So I'm sorry it has to be so quick. My time must be about up. It was recommended by our noble leader that we should identify topics on her list, on the list. Key challenges, here they are. We're dealing with the nature of matter, and recall that nuclei account about for 99.5% of the mass of the universe. That's actually higher than what I said on the first slide. Why does it matter? It's the ultimate source of energy in the universe. It's Quark's to cosmos concept. Why blue waters? Blue waters, we've tried them all. Hopper, Titan, Mara. Blue waters is in our sweet spot because it has robust cores. It has large memory cores. And it has a lot of cores. And it works extremely well for this particular problem. We've used it. It's a nice machine. To date, many papers, plus pushing beyond the reach of other competitive theories. Lots of PRLs out there that we've been able to generate. Blue Water team contributions, excellent support and guidance as needed. I would say that anytime we needed some help, we've always gotten it, particularly from the Blue Waters team. We certainly appreciate that. We don't have time to know all the idiosyncrasies of the machine, so the team that you have in place is great. Broader impacts, training of next generation STEM, you usually hear, but this day and age it's STEAM. Science, technology, engineering, arts, and math. The arts are getting into the game, and it's playing an important role for us. Everything is shared. It's publicly available, even the codes. And the products, well, next generation no-core shell model, called it symmetry-adapted no-core shell model. To date, we grew up on the Lonnie machines at LSU, Louisiana. We moved to the Texas machines. From there, we went to Hopper. From there, we went to Titan and ended up on Blue Waters. Not heavy production yet. In fact, the slides that we saw last night in nuclear physics, I was embarrassed because we didn't even have 1% of the total usage. Hopefully that will change. To date, here's what we've gotten. We just got 600 node hours, 600,000 node hours, which we've already used a good chunk of. And of course, there's a proposal in waiting for us. So that's real briefly the story of what we are doing with the extended LSU team in the area of symmetry-adapted no-core shell model. And I take any questions if you have it.